The Era of Innovation and the Conglomerate, 1930 to 2000. The history of Texas Instruments, TI, is not merely a corporate chronicle. It is a geological cross-section of the 20th century American industrial experience. Born in the depths of the Great Depression as a service provider for the petroleum industry, the entity that became Texas Instruments evolved into a defense contractor during the existential threat of World War II, transformed into a consumer electronics titan during the post-war boom, and finally emerged as a specialized semiconductor powerhouse at the dawn of the millennium. This review offers an exhaustive analysis of TI's trajectory from 1930 to 2000, examining the strategic pivots, engineering breakthroughs, and cultural dynamics that propelled a Dallas-based seismic crew to the vanguard of the global information revolution. Unlike the fair children of Silicon Valley, companies spawned directly from the semiconductor prowess of Fairchild Semiconductor, TI's DNA was distinctly Texan, rugged, pragmatic, and rooted in the earth sciences. Its founders were not initially seeking to miniaturize electronics, they were seeking oil. This foundational difference imbued the company with a penchant for vertical integration and a wildcatter's appetite for risk, traits that would define its aggressive entry into markets ranging from transistor radios to home computers. The narrative of TI is dominated by the tension between innovation and conglomeration. For decades, the company operated on the belief that it could dominate every link in the value chain, from growing the silicon crystal to manufacturing the final calculator or missile that used it. This philosophy, championed by leaders like Patrick Haggerty and Mark Shepard, produced world-changing inventions like the silicon transistor and the integrated circuit. However, it also led to the conglomerate era, a period of sprawling diversification that ultimately proved unsustainable in the face of specialized global competition. By tracing the company's evolution through the four fathers, the tyranny of numbers, the home computer wars, and the brutal trade disputes with Japan, this review elucidates how Texas Instruments engineered the modern world, lost its way in the wilderness of diversification, and drastically restructured itself to survive the 21st century. The Science of Echoes, 1930 to 1941. The story of Texas Instruments begins in the oil fields of Oklahoma and Texas, not with a microchip, but with a stick of dynamite. In the early 20th century, oil exploration was largely a game of educated guesswork and surface geology. By the late 1920s, however, the easy oil was gone, and the industry needed a way to see beneath the surface. In 1930, two physicists, Dr. J. Clarence Karcher and Eugene McDermott, founded Geophysical Servicing, or GSI. Their venture was predicated on Karcher's development of reflection seismology. Unlike the prevailing refraction methods, which measured sound waves bending around subsurface rock layers, Karcher's technique measured the waves that bounced off them. By detonating explosives on the surface and recording the returning echoes with sensitive geophones, GSI could create a three-dimensional map of subterranean geology, identifying the salt domes and anticlines where oil was likely to hide. Launching a capital-intensive service business in 1930, the first full year of the Great Depression, was an act of supreme optimism. Karcher served as the scientific visionary, while McDermott, a man of relentless energy and practical design skills, managed the equipment and operations. To staff this precarious venture, they recruited a cadre of talented engineers who would become the architects of the company's future. Cecil H. Green, a British-born electrical engineer, and J. Eric Johnson, a mechanical engineer initially hired to run the machine shop, but soon promoted to manage the logistics of GSI's far-flung crews. Throughout the 1930s, GSI revolutionized the oil services industry. It became the first independent contractor to offer reflection seismology, liberating major oil companies from the cost of maintaining permanent exploration departments. GSI crews became a common sight in the oil patches of the American Southwest, the swamps of Louisiana, and eventually international fields in Saudi Arabia and South America. The work was physically demanding and technically rigorous. GSI built its own equipment, trucks, drills, explosives, and recording devices, fostering a culture of self-reliance and vertical integration that would later characterize TI's electronics manufacturing. The company operated on a crew model where small, autonomous teams worked in remote locations, a structure that encouraged independent problem-solving and rapid adaptation. However, the nature of the oil business was cyclical. When oil prices dropped, exploration budgets were the first to be cut, leaving GSI vulnerable. In 1939, to stabilize its finances, the company was reorganized under a parent entity, Coronado Corporation, which diversified into direct oil production. This moved GSI from a pure service provider to a player in the oil market, creating tension with its clients, the major oil companies, who viewed Coronado as a competitor. By 1941, the conflict of interest inherent in the Coronado structure became untenable. The oil assets, Coronado, were sold to Staniland Oil and Gas, later Amoco, but Staniland had no interest in the service arm. This presented an opportunity for the GSI leadership team. On December 6, 1941, a date etched in history for another reason, 4 GSI executives purchased the company from Staniland. These men, known in corporate lore as the Four Fathers of Texas Instruments, were Eugene McDermott, the original co-founder and scientific drive, J. Eric Johnson, the operational genius and future mayor of Dallas, Cecil H. Green, the master of field operations and client relations, and H. Bates Peacock, a key geophysicist and crew manager. They pooled their personal savings and collateral to buy GSI, envisioning a future focused on geophysical services. The very next day, the Japanese bombed Pearl Harbor. The United States entered World War II, and the global oil exploration market evaporated overnight as borders closed and resources were requisitioned for the war effort. The new owners of GSI faced immediate bankruptcy unless they could pivot. The Wartime Pivot and the Foundation of Electronics, 1942 to 1951. The outbreak of war presented an existential threat to GSI, but Johnson and McDermott recognized a lifeline. The physics of oil exploration was remarkably similar to the physics of enemy detection. Both required the generation, detection, and interpretation of signals. GSI aggressively courted government defense contracts. Their breakthrough came with the U.S. Navy, which was losing the Battle of the Atlantic to German U-boats. The Navy needed a way to detect submerged submarines from the air. GSI engineers adapted their knowledge of magnetic fields to manufacture magnetic anomaly detectors, or MADs. These devices, carried aboard low-flying aircraft, detected the minute disturbances in the Earth's magnetic field caused by the steel hull of a submarine. This contract was transformative. It required GSI to transition from batch production of rugged seismic gear to the precision manufacturing of military-grade electronics. It also introduced the company to the rigorous quality standards and administrative complexities of the Department of Defense. The most significant acquisition GSI made during the war was not a contract, but a person. Lieutenant Patrick E. Haggerty, a reserve officer in the Navy's Bureau of Aeronautics, was the technical liaison overseeing GSI's electronics contracts. Johnson was impressed by Haggerty's intellect, his grasp of manufacturing processes, and his visionary ambition. In November 1945, as the war wound down, Johnson persuaded Haggerty to join GSI as the general manager of the newly formed Laboratory and Manufacturing Division, or L&M. Haggerty accepted, but on one condition: the company must commit to becoming a major electronics manufacturer, not just a seismic service provider. Haggerty saw that the skills GSI had acquired in wartime, building radar components and sonar systems, had vast commercial potential. From 1946 to 1950, the company operated as a two-headed entity. GSI continued its global hunt for oil, capitalizing on the post-war boom. Simultaneously, Haggerty's L&M division aggressively pursued defense electronics, securing contracts for radar systems and missile guidance components. Haggerty argued that to succeed in electronics, the company needed scale. He pushed for vertical integration, the control of everything from the raw material to the finished system. This philosophy would become the hallmark of the company. By 1951, the L&M division was growing faster than the geophysical parent. The tail was wagging the dog. To reflect this new reality, the company reorganized. The name General Instruments was chosen but found to be taken. In 1951, the company was renamed Texas Instruments Incorporated, or TI. Under this new structure, GSI became a wholly owned subsidiary of TI. The service company that had birthed the electronics giant was now just a division within it, a symbolic and operational shift that set the stage for the semiconductor revolution. The Silicon Gambit, 1952 to 1957. In 1952, Western Electric, the manufacturing arm of AT&T Bell Labs, announced it would license the patent for the transistor, invented in 1947, for a fee of $25,000. To the established giants of the electronics industry, RCA, GE, Sylvania, the transistor was an interesting but immature technology, likely destined for niche applications like hearing aids. To Patrick Haggerty, it was the future. He convinced the TI board to pay the fee, a substantial sum for a mid-sized defense contractor. But Haggerty knew that holding a license was useless without the know-how to exploit it. He needed a scientist who understood crystal growth at an atomic level. He found Gordon Teal. Teal was a Texan working at Bell Labs who had been instrumental in early transistor research. However, Teal was frustrated by Bell's focus on germanium as the semiconductor material of choice. Germanium was easier to work with, but had a fatal flaw. It stopped working at temperatures above 170 degrees F, approximately 75 degrees C. Teal believed silicon, with its higher melting point and superior electrical properties, was the superior material, but his superiors at Bell were uninterested. Haggerty hired Teal in 1953 to head TI's research lab, giving him a mandate to develop a silicon transistor. The industry's reliance on germanium was a significant bottleneck for military applications. A transistor inside a jet engine or a missile guidance system would essentially melt or suffer from thermal runaway, uncontrollable current flow caused by heat. TI's competitors were locked in a race to improve germanium, but Teal and his team at TI quietly worked on growing pure silicon crystals. The challenge was chemical. Silicon has a high melting point and is incredibly reactive in its molten state. Teal's team had to develop new methods of crystal pulling, the Chostralski process, and doping to create a stable NP-N junction. On May 10, 1954, at the Institute of Radio Engineers conference in Dayton, Ohio, the leading experts of the day presented papers on the limitations of germanium. The consensus was that silicon transistors were theoretically possible, but years away from commercial viability. Teal then took the podium. He read his paper, then announced, "Contrary to what my colleagues have told you about the bleak prospects for silicon transistors, I happen to have a few of them here in my pocket." He pulled out TI's new 900 series silicon transistors and demonstrated a record player that continued to play music even when the amplifier was dunked into a beaker of hot oil. The room erupted. TI was the only company in the world with a commercial silicon transistor. This monopoly lasted for nearly 3 years. TI sold these transistors to the military for $100 to $150 each, over $1,000 in today's money, generating massive profits that funded further R&D. TI had leapfrogged the entire electronics industry. While silicon conquered the military, Haggerty wanted to conquer the consumer. He knew that transistors to replace vacuum tubes universally, their cost had to come down. That required volume, millions of units, which the military alone could not provide. Haggerty conceived of the transistor radio. Vacuum tube radios were portable only in a loose sense. They were heavy, fragile, and devoured batteries. A transistor radio would be pocket-sized and instant on. TI approached major radio manufacturers like RCA and Philco, but they rejected the idea, claiming transistors were too expensive. Undeterred, TI partnered with Industrial Development Engineering Associates, IDEA, a small antenna booster company in Indianapolis. TI would supply the germanium transistors, sufficient for consumer temperatures, and IDEA would build the radio under the Regency brand. The engineering challenge was immense. To hit the target price of $49.95, engineers had to reduce the transistor count from the standard 8 to just 4. This required pushing each component to its limit. The Regency TR-1 launched on October 18, 1954, just in time for Christmas. It was a cultural phenomenon. Available in colors like mandarin red and cloud gray, the TR-1 became a status symbol. It sold 150,000 units in its first year. Critically, it spurred Japanese competitors, notably a small company named Tokyo Tsushin Kugyo, later Sony, to enter the market. The TR-1 did not make TI rich directly, but it created the global demand for semiconductors that Haggerty had predicted. It was the big bang of consumer electronics. The monolithic idea and the tyranny of numbers, 1958 to 1965. By the late 1950s, the electronics industry faced a scaling crisis known as the tyranny of numbers. As military and computing systems demanded more complex circuits, the number of discrete components, transistors, resistors, diodes, capacitors, required to build them skyrocketed. A single advanced circuit might require thousands of components, each of which had to be individually manufactured, tested, and hand-soldered. The resulting systems were heavy, expensive, and unreliable. A system with 100,000 soldered joints had 100,000 potential points of failure. The industry sought solutions in micromodules, Lego-like blocks of components, but this was merely a packaging refinement, not a solution. In 1958, TI hired Jack Kilby, a tall, quiet engineer from Central Lab. Kilby arrived in Dallas in July. Because he had not yet accrued vacation time, he worked through the company's traditional mass shutdown in August. Alone in the lab, he pondered the tyranny of numbers. Kilby realized that TI's expertise lay in semiconductors. He hypothesized that all circuit components, not just transistors, could be fabricated from the same semiconductor material. Resistors could be made from the bulk resistance of the silicon. Capacitors could be formed by p-n junctions. If all components were made of the same block, they could be interconnected internally, eliminating the wires. On September 12, 1958, Kilby presented his boss with a crude prototype, a sliver of germanium glued to a glass slide with protruding wires held by wax. When voltage was applied, the oscilloscope displayed a continuous sine wave. The device worked. It was the world's first integrated circuit. While Kilby had the first working prototype, Robert Noyce at Fairchild Semiconductor in California was independently developing a similar concept. Noyce's version used silicon and a planar process where connections were made by depositing metal layers on top of the chip, a much more practical method for mass production than Kilby's flying wires. A decade-long legal battle ensued over who invented the IC. The stakes were billions of dollars in future royalties. Ultimately, the courts and the companies agreed to cross-license the patents. Kilby and Noyce are now recognized as co-inventors. This patent portfolio would become one of TI's most lethal strategic weapons in the 1980s. Just as with the transistor, the early IC was prohibitively expensive, $100 plus per chip. Once again, TI turned to the U.S. Air Force. The Minuteman II missile program needed a guidance computer that was light enough to fly and reliable enough to survive a nuclear launch. TI lobbied hard and won the contract to supply ICs for the Minuteman. This volume commitment allowed TI to refine its manufacturing yield, driving costs down. Similarly, TI components became integral to the Apollo program, with TI engineers ensuring that the guidance systems for the lunar modules were robust. By 1965, driven by these government contracts, the price of an IC had dropped to under $10, opening the door for commercial applications. The Conglomerate era and consumer dominance, 1967 to 1979. In 1967, Patrick Haggerty challenged Jack Kilby to invent a slide rule replacement, a handheld electronic calculator. The Caltech project resulted in a prototype that could add, subtract, multiply, and divide. Initially, TI partnered with Canon to sell the Pockettronic in 1970, but soon TI decided to enter the market itself. The launch of the TI 2500 Datamath in 1972 marked a pivotal shift. TI was no longer just a chip supplier, it was a consumer brand. This move leveraged TI's philosophy of vertical integration. By manufacturing the chips, the displays, the keyboards, and the final assembly, TI could undercut any competitor who had to buy parts from suppliers. TI engaged in a ruthless price war. In 1972, a calculator cost $150. By 1976, TI was selling them for $20. Competitors like Bomar, which had pioneered the market but relied on purchasing chips, often from TI, were driven into bankruptcy. TI captured the market, establishing the brand dominance that persists in education today. The architect of this aggressive expansion was Mark Shepard, who became CEO in 1969. Shepard, a formidable and demanding leader, implemented a management system called OST, Objectives, Strategies, and Tactics. This system was designed to align the massive conglomerate's diverse goals. While effective initially, OST eventually calcified into a bureaucratic nightmare. Managers spent months preparing strategy documents rather than executing them. This rigidity, combined with a brutal up-or-out personnel policy, created a high-pressure environment. Engineers were pitted against one another. Success brought rapid promotion, while failure led to dismissal. This Darwinian culture drove short-term performance, but began to erode long-term morale and retention. In 1978, TI introduced the Speak and Spell, an educational toy that could synthesize human speech. It was powered by the TMS 5100, the first linear predictive coding speech synthesizer chip. While marketed as a toy, the Speak and Spell was a Trojan horse for a revolutionary technology: digital signal processing, DSPs. DSPs are specialized microprocessors designed to manipulate real-world signals, sound, radio waves, and images in real time. This technology, incubated in a child's toy, would eventually become the cornerstone of TI's dominance in the mobile phone era of the 1990s and 2000s. The hubris of the home computer, 1979 to 1983. Emboldened by its victory in calculators, TI targeted the nascent home computer market. In 1979, it released the TI-99/4, the world's first 16-bit home computer. It was technically superior to the 8-bit Apple II and Commodore PET, but it was hobbled by a terrible chiclet keyboard and a high price, $1,150. TI iterated quickly, releasing the TI-99/4A in 1981 with a better keyboard and improved graphics. It initially sold well, capturing over 35% of the market. However, TI's strategy of keeping the architecture closed to force customers to buy TI peripherals alienated third-party developers, unlike the open ecosystems of Apple and later IBM. TI soon faced Jack Tramiel of Commodore. Tramiel, who had been nearly destroyed by TI during the calculator wars, sought revenge. He launched a brutal price war, famously saying, "Business is war." Every time TI lowered the price of the 99/4A, Commodore undercut them with the VIC-20 and Commodore 64. TI's vertical integration, once a strength, became a liability. The 99/4A was expensive to manufacture due to its complex architecture and reliance on specific TI chips. Commodore, which owned MOS Technology, chipmaker, had a cheaper, simpler design. By 1983, TI was forced to sell the 99/4A for under $100, losing money on every unit. The anticipated profit from software cartridges never materialized to cover the hardware losses. In October 1983, TI announced a stunning loss of $330 million for the year and exited the home computer market entirely. It was a humiliating defeat that shattered the company's aura of invincibility and exposed the flaws in the OST management system and the conglomerate model. The upper-out culture and the brain drain. The internal culture of TI during the Shepard-Busey era was characterized by the up-or-out policy. This unwritten but pervasive rule dictated that employees must constantly advance to higher levels of responsibility. Those who plateaued, even competent, valuable engineers, were often pushed out or marginalized. This created a fierce internal competition. While it drove rapid execution, it also discouraged risk-taking in unproven areas. Managers would hoard resources for safe projects that fit the OST metrics, while visionary but risky ideas were starved. The most consequential casualty of this culture was Morris Chang, a brilliant executive who had run TI's entire semiconductor group. Chang was seen as a potential CEO. However, he clashed with the Shepard-Busey leadership over the company's strategic direction, particularly the obsession with consumer products at the expense of semiconductor innovation. In 1983, feeling put out to pasture in a staff role and hitting the plateau that the upper-out culture disdained, Chang resigned. He was recruited by the Taiwanese government to build their electronics industry. In 1987, Chang founded TSMC, Taiwan Semiconductor Manufacturing Company, pioneering the foundry model, manufacturing chips for other companies without designing them. TI's loss was Taiwan's gain. TSMC grew to become the most important semiconductor company in the world. Had TI's culture been more flexible, Chang might have pioneered the foundry model within TI, potentially altering the entire geopolitical landscape of the 21st century. The Japanese Threat and the Patent Weapon, 1985-1990. By 1985, TI faced a new crisis, the Japanese onslaught in memory chips. Japanese conglomerates like Hitachi, NEC, and Toshiba, supported by government subsidies, flooded the global market with DRAM chips. They sold these chips below the cost of production, dumping, to drive US firms out of the market. The strategy worked. Intel exited the memory business in 1985. Most US memory makers collapsed. TI, however, refused to yield. Having established a manufacturing plant in Japan in 1968, a hard-won concession, TI understood the Japanese cost structure better than its peers and knew the dumping was predatory. In 1985, TI posted its first ever annual loss, $145 million. The company was bleeding cash. TI led the lobbying effort via the Semiconductor Industry Association, SIA. Mark Shepard used his position on the Reagan administration's Competitiveness Commission to argue that domestic semiconductor manufacturing was a national security imperative. This pressure led to the 1986 US-Japan Semiconductor Trade Agreement. The pact forced Japan to stop dumping and to open 20% of its market to foreign chips. While controversial, it stabilized prices, giving TI the breathing room to survive. Facing financial ruin, TI unleashed a new weapon, its patent portfolio. TI lawyers realized that virtually every modern electronic device infringed on TI's foundational patents, including the Kilby IC patent. TI launched an aggressive litigation campaign against Japanese and Korean firms. The message was simple: pay a royalty or be banned from the US market. The strategy was wildly successful. Between 1986 and 1993, TI generated over $1.5 billion in patent royalties. In several years, this pure profit exceeded the company's operating income from product sales. This capital infusion kept the R&D engines running during the darkest days of the memory crisis. The Junkins era and the strategic pivot, 1985 to 1996. When Fred Busey resigned abruptly in 1985, Jerry Junkins became CEO. Junkins was a TI lifer, but possessed a markedly different style. He dismantled the bureaucratic OST system and softened the up-or-out culture, emphasizing teamwork, diversity, and employee empowerment. He sought to make TI a human place again. Junkins also championed Total Quality Management, or TQM. Recognizing that Japanese manufacturing quality had surpassed the US, he instigated rigorous quality controls. This culminated in TI's defense group winning the Malcolm Baldrige National Quality Award in 1992, a massive validation of the company's turnaround. Despite the cultural turnaround, TI was still a sprawling, unfocused conglomerate. Junkins and his team realized that to win in the 1990s, they had to specialize. They identified digital signal processors, or DSP, and analog chips as the company's crown jewels, high-margin products where TI had a distinct engineering lead. This led to a painful but necessary series of divestitures. Geophysical Service Inc., GSI. In 1988, TI sold 60% of its founding business to Halliburton, severing the company's emotional connection to the oil industry. Defense Systems. In 1997, following Junkins' sudden death in 1996, TI sold its highly profitable defense business, makers of the HARM missile and Paveway bombs, to Raytheon for $2.95 billion. Memory, or DRAM. In 1998, TI sold its memory business to Micron, finally exiting the commodity market that had caused so much pain. By the year 2000, Texas Instruments had completed one of the most successful corporate transformations in history. The conglomerate that once drilled for oil, built missiles, and sold home computers was gone. In its place stood a lean, highly profitable semiconductor company focused on analog and DSP chips, the essential components of the mobile phone and internet revolution. TI's history is a testament to the power of innovation, the IC, the silicon transistor, and the necessity of strategic discipline. The company survived the up-or-out culture wars, the Japanese trade assault, and the collapse of its consumer business by willing to cannibalize its past to secure its future. The oil men of 1930 would hardly recognize the silicon giant of 2000, but the spirit of the wildcatter, the willingness to drill a hole in the ground on a hunch, remained alive in the microscopic architecture of its chips. The analog transformation, capital discipline, and geopolitics, 2000 to present. In the high-velocity, high-stakes universe of semiconductor manufacturing, where the industry narrative is frequently dominated by the relentless pursuit of Moore's law, artificial intelligence accelerators, and nanometer-scale logic races, Texas Instruments, TI, presents a formidable counter-narrative. It is a corporate entity that has systematically engineered its own stability, transforming from a broad-based, volatile electronics conglomerate into a disciplined, high-margin analog monopoly in all but name. This part provides an exhaustive analysis of Texas Instruments' strategic evolution from the year 2000 to the present day, documenting a corporate metamorphosis that stands as a paramount example of long-term capital allocation, industrial foresight, and geopolitical maneuvering. The transformation of Texas Instruments is not merely a chronicle of technological innovation, though the company's history of invention, from the integrated circuit to the handheld calculator, is foundational. Rather, the modern history of TI is a masterclass in financial engineering and operational rigor. Under the architectural guidance of Tom Engibus and the relentless execution of Rich Templeton, TI executed a great strategic pivot, deliberately exiting the glamorous but commoditized DRAM memory market and the high-volume but margin-compressing mobile processor sector. In their place, the company constructed a fortress around the seemingly mundane but profoundly profitable world of analog and embedded processing chips, components that obey the laws of physics rather than the dictates of consumer fashion. This part dissects the mechanisms of this transformation with granular precision. It analyzes the specific financial structures of the DRAM divestiture to Micron and the die bank strategy that allows TI to buffer against industry cyclicality. It details the strategic acquisition of National Semiconductor, which consolidated TI's market leadership and expanded its catalog breadth to unassailable levels. It explores the company's contrarian multi-decade bet on 300mm wafer manufacturing for analog chips, a decision that grants TI a structural cost advantage of approximately 40% over competitors relying on older 200mm technology. Furthermore, we examine TI's aggressive restructuring of its sales channels, moving away from distribution partners like Avnet and Arrow to a direct-to-customer model via TI.com, thereby capturing greater margin and, crucially, retaining ownership of customer data. The part also contextualizes TI's recent massive capital expenditure roadmap, over $30 billion committed to new fabrication facilities in Sherman, Texas and Lehi, Utah, within the framework of the U.S. CHIPS and Science Act. As geopolitical tensions between the U.S. and China rise, TI has repositioned itself not just as a chip vendor, but as a provider of geopolitically dependable capacity for the industrial and automotive sectors that form the backbone of the Western economy. Through a synthesis of financial filings, historical data, and strategic actions, this part illuminates how Texas Instruments has engineered a business model that prioritizes longevity, reliability, and cash generation over the ephemeral spikes of the hype cycle, creating a capital allocation machine that has returned vast sums to shareholders while securing its industrial future. The Great Strategic Pivot, 2000 to 2012. The turn of the millennium marked a precarious and pivotal era for Texas Instruments. While the company possessed a storied history, inventing the integrated circuit in 1958 and the handheld calculator in 1967, its portfolio in the late 1990s was a sprawling, incoherent mix of defense electronics, software, memory chips, and digital signal processors, DSPs. The strategic pivot executed between 2000 and 2012 was not a single event, but a sequence of calculated divestitures and acquisitions designed to reduce volatility and increase the quality of the company's revenue. This era defined the TI of today, a company that refuses to chase revenue for revenue's sake, prioritizing instead the quality of earnings and the sustainability of margins. To understand the modern trajectory of Texas Instruments, one must first understand the trauma and the lessons of the DRAM, Dynamic Random Access Memory market. Throughout the 80s and 90s, memory chips were the crude oil of the technology world, essential, ubiquitous, but subject to brutal boom and bust cycles driven by global capacity gluts and fierce price wars, particularly from aggressive Japanese and Korean competitors. In 1998, the semiconductor industry faced a deep trough in the memory cycle. Prices for some popular DRAM configurations collapsed by nearly 95% over a 2-year period, decimating margins for all players involved. For TI, the volatility of DRAM earnings was a constant drag on the company's valuation, obscuring the consistent high-margin performance of its growing digital signal processor, DSP, and analog businesses. The architect of the exit, then CEO Tom Engebus, recognized a fundamental flaw in the DRAM business model. The capital intensity required to compete, constantly building new fabs to shrink transistors and increase density, yielded diminishing returns on invested capital. In a commoditized market, the player with the lowest cost of capital and the highest tolerance for pain wins. TI, with its focus on innovation and diversified electronics, was ill-suited for this race to the bottom. The decision to exit DRAM was radical. In a complex transaction that set the precedent for TI's future financial engineering, the company sold its memory assets to Micron Technology. This sale included wafer fabrication facilities in Avezzano, Italy, Richardson, Texas, formerly known as Twin Star, and joint ventures in Singapore and Japan. The structure of the deal reveals TI's priority, strictly limiting liability and securing future upside without capital commitment. Micron assumed $190 million in government-sponsored debt associated with TI's Italian operations and received $750 million in financing from TI to upgrade the facilities. In return, TI received approximately $880 million in Micron convertible notes and equity, plus a 10-year royalty-free patent cross-license agreement. This was the patient zero moment for TI's modern capital allocation strategy. By exiting DRAM, TI eliminated its largest source of capital expenditure unpredictability. It signaled to Wall Street that TI would no longer chase revenue share in commoditized markets where it held no pricing power. Instead, capital would be redirected towards DSPs and analog, where product life cycles were longer, engineering expertise provided a moat against price erosion, and customer relationships were stickier. This move transitioned TI from a chip manufacturer to a solutions provider, fundamentally altering its risk profile. If the DRAM exit was about escaping a commodity trap, The exit from mobile processors, OMAP, was about escaping a sexy trap, the allure of high-volume consumer electronics that ultimately destroys shareholder value through relentless R&D requirements and margin compression. In the early 2000s, TI was the undisputed king of mobile. Its OMAP processors powered the most iconic devices of the era, from Nokia's dominant handsets to the early Motorola Droid and the Palm Pre. As the smartphone revolution ignited by the iPhone took hold, the market volume exploded, promising unprecedented revenue growth. However, the structural dynamics of the mobile market began to shift unfavorably for merchant silicon vendors like TI. Vertical integration. Major OEMs like Apple and Samsung began designing their own chips, Apple Silicon, Exynos, removing the most lucrative customers from the merchant market. Modem integration. Qualcomm used its dominance in baseband radios, CDMA, LTE patents, to integrate the application processor with the modem into a single system-on-chip, SoC. This integration saved board space and power, creating a compelling value proposition that standalone processor makers like TI struggled to match. The gigahertz race, the arms race for higher clock speeds and core counts, required massive, recurring R&D investment to move to 28 nanometers, 20 nanometers, and beyond. This investment had to be amortized over a shrinking customer base. By 2012, TI faced a critical decision point. Staying competitive in mobile required doubling down on R&D for a market where they had lost pricing power. Staying would mean chasing revenue growth at the expense of profitability. In September 2012, TI announced it would halt investment in OMAP for smartphones and tablets. The company pivoted the OMAP technology towards embedded applications in automotive and industrial markets, sectors where product life cycles are measured in decades, not months, and where customers value reliability and support over raw benchmark scores. This move was initially viewed with skepticism by tech enthusiasts and some analysts, who saw mobile as the only growth engine in semiconductors. However, TI's leadership realized that while mobile offered volume, it did not offer value commensurate with the required R&D. By pivoting OMAP technology to automotive, e.g. automotive infotainment systems, advanced driver assistance systems, TI repurposed its IP for a market with higher barriers to entry. In the automotive sector, once a chip is designed into a braking system or a dashboard, it remains there for the life of the vehicle platform, often 10 years or more, generating an annuity-like stream of cash flow with zero additional sales effort. While shedding volatile businesses, TI aggressively expanded its footprint in the high-quality analog market. The crown jewel of this expansion was the 2011 acquisition of National Semiconductor for $6.5 billion in cash. At the time, TI was already the market leader in analog, with about 14% market share. National Semiconductor was a strong player in industrial power management, but lacked TI's massive sales force and manufacturing scale. The acquisition was a classic consolidation play, bringing 12,000 analog products under the TI umbrella. TI's sales force was 10 times larger than National's. By plugging National's portfolio into TI's global distribution machine, TI could immediately accelerate sales of National's parts to a broader customer base, particularly in Asia, where TI had a stronger foothold. TI systematically migrated National's production from older external foundries or less efficient fabs into its own burgeoning 300mm manufacturing network. This migration extracted significant cost synergies, improving the gross margin profile of the acquired products. The combined portfolio reached nearly 45,000 analog products. In the analog world, breadth is a massive competitive advantage. Engineers prefer to source multiple components, power regulators, amplifiers, data converters, from a single supplier to simplify supply chain management and ensure design compatibility. This acquisition cemented TI's strategy: dominate the fragmented, high-margin analog market, where no single customer, like Apple in mobile, possesses enough leverage to dictate terms. It transformed TI into a supermarket for analog chips, essential to every electronic device, but reliant on none. The transformation was driven by two distinct leaders who acted in concert across 2 decades. Tom Angabus, CEO 1996 to 2004, the architect of the pivot. Angabus made the hard calls to exit the defense business and DRAM, dismantling the conglomerate structure and laying the foundation for a pure-play semiconductor company. His vision was strategic clarity, focusing only on businesses where TI could lead. Rich Templeton, CEO 2004 to 2023, the executor. Templeton is widely regarded as one of the most disciplined capital allocators in corporate history. Under his tenure, the focus shifted relentlessly to free cash flow per share. He operationalized the analog strategy, overseeing the national acquisition and the transition to 300mm manufacturing. His leadership style was characterized by an aversion to hype and a devotion to operational metrics. He eschewed the moonshot culture of Silicon Valley for a culture of incremental compounding improvement, the grind of selling 80,000 distinct products to 100,000 customers. Business model and financial strategy: the capital allocation machine. Texas Instruments does not view itself merely as a technology company. It operates as a financial engine designed to maximize the long-term growth of free cash flow per share. This metric is the prime directive of TI's corporate governance, explicitly stated in nearly every investor presentation for the last 2 decades. This unwavering focus distinguishes TI from peers who may prioritize revenue growth, market share, or technological prestige. TI's business model is structured to generate cash with high efficiency and predictability. The mechanics are distinct from digital logic companies like NVIDIA or Intel and rely on the unique characteristics of the analog market. Analog chips, examples power management, sensors, operational amplifiers, deal with real-world signals like sound, temperature, and pressure. These physical properties do not change. Consequently, a voltage regulator designed in 2010 might still be perfectly adequate for a washing machine or an industrial robot manufactured in 2024. This allows TI to sell the same product for 10 to 20 years, amortizing the R&D and manufacturing equipment costs over extremely long periods. This contrasts sharply with digital logic, where a chip is obsolete in 18 months. TI serves over 100,000 customers across industrial, automotive, personal electronics, communications, and enterprise systems sectors. No single customer creates a dependency risk. This fragmentation insulates TI from the hit-driven nature of consumer electronics. Even if a major smartphone manufacturer fails, TI's exposure is limited. By focusing on differentiated industrial and automotive applications, TI maintains high gross margins, consistently in the 60 to 70% range in recent years. These margins are protected by the high switching costs in industrial applications. An engineer is unlikely to redesign a functioning factory control board to save 10 cents on a power chip. This engine generates robust operating cash flow. In 2024, TI ranked in the 88th percentile of the S&P 500 for operating cash flow as a percentage of revenue. TI's approach to deploying this cash is strictly formulaic and disciplined. Invest in the business, R&D and CapEx, to sustain organic growth and extend competitive advantages. Return all remaining cash to shareholders via dividends and buybacks. Between 2004 and 2024, TI reduced its outstanding share count by 47%. This massive reduction means a long-term shareholder owns nearly double the percentage of the company today compared to 2004, without buying a single additional share. Unlike many tech companies who buy back stock only when flush with cash, often at market peaks, to offset stock-based compensation dilution, TI has been a consistent, price-agnostic buyer through all market cycles. They view their own stock as the best risk-adjusted return on investment available, effectively privatizing the company over time for the benefit of remaining shareholders. TI has increased its dividend for roughly 22 consecutive years, 2004 to 2024, with a compound annual growth rate of 23%. This streak places TI among the elite dividend aristocrats of the tech sector. The commitment to dividends imposes fiscal discipline on management. Because the cash must go out the door, there is less temptation to squander it on ill-advised empire-building acquisitions or low-return projects. A unique, often misunderstood aspect of TI's financial strategy is its inventory management. In the general semiconductor industry, inventory is usually seen as a liability. Chips become obsolete quickly, and holding them ties up working capital. TI takes a contrarian view, treating inventory as a strategic asset. TI utilizes a die bank strategy. It manufactures wafers, the die, and stores them in a semi-finished state before packaging. A significant portion of reported inventory is WIP, work in process, wafers that have completed the front-end fabrication but have not been cut and packaged into final black plastic chips. Storing inventory at the die level allows TI to be flexible. A single die design might be used in multiple final product variations, different voltage ratings, different package types. By holding the die, TI can package it to order based on real-time demand signals. Because analog products have life cycles measuring decades, the risk of the inventory becoming worthless is negligible. A power chip sitting in a die bank for 2 years is just as valuable as one made yesterday. TI builds inventory during downturns, when fabs are underutilized and unit costs would otherwise rise due to fixed cost absorption, to be ready for the inevitable upturns. In the post-COVID supply chain crisis, this strategy paid dividends. While competitors scrambled for capacity, TI had inventory reserves that allowed them to support key industrial and automotive customers, strengthening relationships and gaining market share. In Q3 2025, for instance, TI maintained inventory days at 215, deliberately higher than the industry average, in order to ensure high levels of customer service. This ability to supply product when others cannot is a form of reliability premium that TI charges for. Manufacturing and investments, the fab strategy. Unlike fabless competitors such as Qualcomm, Broadcom, and NVIDIA, who outsource manufacturing to foundries like TSMC, TI adheres to a model of vertical integration. They believe that owning their manufacturing capacity provides a dual advantage: lower costs and supply assurance. The cornerstone of TI's manufacturing strategy is the aggressive transition to 300mm wafers for analog production. This is a strategy that TI pioneered and continues to lead. A 300mm or 12-inch wafer has 2.25 times the surface area of a standard 200mm or 8-inch wafer used by most analog competitors. The cost to process a wafer, chemicals, gas, time, is roughly the same regardless of size. Therefore, producing chips on a 300mm wafer dramatically increases the number of chips per batch, reducing the cost per individual chip by approximately 40% compared to 200mm production. Historically, 300mm fabs were reserved for expensive digital logic, CPUs and GPUs, because filling a 300mm fab requires massive volume. Analog chips are small and cheap. Filling a mega fab with them requires billions of units. TI, with its catalog of 80,000 products and massive market share, is one of the few analog companies with the volume to justify 300mm economics. TI kickstarted this strategy by purchasing widely available used 300mm equipment, often from memory companies exiting the market or logic companies upgrading to newer nodes for pennies on the dollar. They equipped their first major 300mm analog fab, R-Fab, Richardson Fabrication, which opened in 2009, with this depreciated gear. This gave them a leading-edge cost structure with a trailing-edge capital cost foundation. In the post-2020 era, facing a structural increase in semiconductor demand from the electrification of vehicles and industrial automation, TI has doubled down on this strategy with an aggressive capital expansion plan. They have outlined a roadmap to invest $5 billion annually in CapEx through 2026. TI is constructing a potential 4-fab mega-campus SM1, SM2, SM3, SM4 in Sherman, Texas. This greenfield investment is one of the largest economic projects in Texas history, designed to support demand for decades. TI acquired a 300mm fab from Micron, L-Fab, in Lehi, Utah, for $900 million in 2021, a fraction of the cost to build a new fab. This purchase was opportunistic. Micron was exiting the 3D XPoint memory business, and TI stepped in to buy the fully built asset. TI is now expanding this site with a second fab, L-Fab 2. By 2030, TI aims to manufacture 95% of its wafers internally, up from roughly 80% in 2020. This insulates TI from the pricing whims of external foundries, like TSMC raising prices, and allows them to control their own supply chain destiny, a critical selling point to automotive customers burned by the 2021 chip shortage. The supply chain revolution. Direct sales. Manufacturing is only half the operational equation. Distribution is the other. Historically, the semiconductor industry relied heavily on distribution intermediaries, companies like Avnet and Arrow Electronics, to manage the long tail of thousands of smaller customers. These distributors held inventory, managed logistics, and extended credit. Starting around 2019, TI began a quiet revolution. It started aggressively cutting ties with these distributors to implement a direct sales model. By late 2019, TI notified Avnet that it would discontinue their relationship, a move that sent shockwaves through the channel. By cutting out the middleman, TI captures the distributor's margin. While TI takes on the cost of logistics, the net benefit to gross margin is positive. In the distribution model, the manufacturer ships to the distributor and loses visibility until the distributor reports a sale. In the direct model, TI holds the inventory. This allows for better global allocation. If a part is needed in Germany, TI doesn't have to worry that the inventory is stuck in an Avnet warehouse in Hong Kong. Most importantly, selling directly via TI.com gives TI granular visibility into real-time demand. Instead of receiving aggregated orders, TI sees exactly who is buying what, when, and for which project. This data is invaluable for demand forecasting and inventory management, the die bank. To support this shift, TI invested heavily on its online presence, turning TI.com into a full-service e-commerce platform. Engineers can buy small quantities for prototyping, download datasheets, use design simulation tools, Webench, and seamlessly transition to volume orders. By 2024, approximately 80% of TI's revenue was transacted directly, a massive shift from 33% in 2019. This transition caused short-term friction with customers accustomed to their distributor reps, but it has structurally improved TI's margin profile and customer intimacy. It essentially digitized the analog buying process, creating a stickier ecosystem where the engineer's workflow is tied directly to the supplier. Politics and the CHIPS Act, the geopolitical hedge. As the U.S. government woke up to the strategic vulnerability of semiconductor supply chains centered in East Asia, Texas Instruments positioned itself as the poster child for American semiconductor independence. While companies like Intel and TSMC garnered headlines for leading-edge logic, TI successfully argued that foundational, analog, or embedded chips are equally critical to national security. TI was heavily involved in shaping the CHIPS and Science Act of 2022. Lobbying disclosures reveal TI spent substantial sums advocating for specific provisions that would benefit mature node manufacturing, ensuring the subsidies weren't monopolized by leading-edge logic. TI specifically supported the Building Chips in America Act, S-2228, a bill designed to streamline federal environmental reviews, NEPA, for semiconductor projects. The argument was pragmatic. If the CHIPS Act is about speed and urgency, then redundant environmental reviews that delay fab construction by years are counterproductive. This legislative maneuvering demonstrates TI's sophisticated understanding of the regulatory landscape. They didn't just ask for money, they asked for the regulatory clearance to spend it efficiently. TI markets itself to customers as a provider of geopolitically dependable capacity. This phrase is a calculated marketing tool. It implicitly contrasts TI with competitors who rely on supply chains in Taiwan or China, which are perceived as vulnerable to geopolitical disruption or blockade. This pitch is particularly effective in the automotive and industrial sectors, TI's core markets. For a car manufacturer, a $1 chip halting a $50,000 production line is a nightmare scenario, as seen in 2021. TI sells not just a chip, but insurance against that nightmare. By building fabs in Texas and Utah, TI effectively sells sovereign supply to global multinationals. TI's strategy bore fruit in August 2024, when it signed a preliminary agreement with the U.S. Department of Commerce for up to $1.6 billion in direct funding under the CHIPS Act. However, the bigger prize is the investment tax credit. The ITC allows TI to deduct 25% of the cost of new equipment and facilities from their federal taxes. For a company projecting $5 billion a year in CapEx, this tax credit is worth $6 to $8 billion over the life of the projects. This subsidy effectively lowers the capital intensity of TI's expansion, improving the long-term return on invested capital, or ROIC, of the new fabs. Despite this America First manufacturing narrative, TI remains deeply entangled with China. In 2024, China accounted for 19.26% of TI's revenue, down from 24% in 2022, but still a massive portion of the business. TI is walking a geopolitical tightrope. It uses revenue from the Chinese market to fund the construction of U.S. fabs that are designed, in part, to insulate the West from China. This creates a risk. If China retaliates against U.S. tech companies, for example, banning TI chips in favor of domestic alternatives, TI's revenue engine could sputter, threatening the free cash flow model that funds the U.S. expansion. However, TI's dominance in analog makes it harder to replace than digital logic vendors. Chinese domestic analog competitors are improving, but still lag in breadth, reliability, and precision for high-end industrial applications. Human resources and modern culture, the engineer's engineer. The culture of Texas Instruments is distinct from the move fast and break things ethos of Silicon Valley. It is a culture of reliability, tenure, and incrementalism, reflecting its industrial customer base. TI values internal promotion and long tenure. Rich Templeton spent his entire career at TI. His successor, Haviv Ilan, who became CEO in 2023 and will assume the chairman role in 2026, is a 26-year veteran of the company. This continuity ensures that the strategic vision, FCF growth, 300mm manufacturing, analog focus remains consistent across decades. The leadership transition was described as well-planned, typical of TI's aversion to surprises. The board of directors is structured to support this long-term view, insulating management from short-term activist pressure. While Elliott management has recently engaged with TI regarding its capex spending, the company has largely maintained its course, arguing that the long-term capacity is non-negotiable. TI engineers are culturally distinct. The company employs a technical ladder system that allows engineers to advance in career status, influence, and pay without becoming managers. An elected senior fellow at TI commands the same respect and compensation as a vice president. This system is critical for retention in analog design. Unlike digital design, which is heavily automated, analog design is often considered a black art, requiring years of apprenticeship and intuition. Losing a senior analog designer is a massive loss of institutional knowledge. The technical ladder ensures these individual contributors have a path to the top, reinforcing a culture where technical excellence is valued as highly as management capability. The pivot from OMAP, consumer mindset, to analog and embedded, industrial mindset, required a profound shift in engineering philosophy. Consumer mindset, time to market is everything. A chip only needs to last 3 to 4 years, the life of a phone. Good enough is acceptable if it hits the launch window. Industrial mindset, reliability is everything. A chip must perform flawlessly for 15+ years in harsh environments, heat, vibration, voltage spikes. Failure is not an option. TI successfully transitioned its workforce by retraining engineers and changing incentive structures to prioritize robustness and longevity over raw speed. This industrial-grade culture is now a defensive moat. Competitors trying to enter the auto market from the consumer space, like NVIDIA or Qualcomm, face a steep learning curve in meeting these reliability standards. In recent years, TI has formalized its diversity and inclusion efforts. As of 2024, the workforce was 22.4% female and 77.6% male. While these numbers reflect the broader gender gap in electrical engineering, TI's emphasis on growing their own talent implies that D&I initiatives are focused on the entry-level pipeline. TI invests heavily in STEM education programs, such as high-tech high heels, to widen the funnel of future female engineers. The company tracks diversity metrics for its board of directors as well, which is 30.8% female and 15.4% Black or African American, reflecting a governance structure that is slowly modernizing. From 2000 to the present, Texas Instruments transformed itself from a volatile, diversified electronics company into a disciplined, focused, and highly profitable analog semiconductor monopoly in all but name. Texas Instruments demonstrates that in the technology sector, being boring is often the most profitable strategy. By pivoting away from the volatility of memory and mobile processors, TI built a business model based on the immutable laws of analog physics and the compounding power of capital allocation. Its current bet on US-based 300mm manufacturing is a strategic hedge against a fragmenting global order, positioning the company to remain the backbone of the electronics industry for decades to come. History suggests that betting against TI's long game and its relentless cash flow engine is a losing proposition.